the future, I see a new class of chip, one inspired by the human brain, unlocking new possibilities and making the world smarter and more connected. To me, this is the next evolution's intelligence with neuromorphic computing will need define what possible. Self-learning neuromorphic chips will transform education, facial recognition, manufacturing, emergency service, smart cities. It's already here. Today we are going to explore a fascinating breakthrough in technology called neuromorphic computing. It's a completely different way of building computers, one that doesn't just calculate like machine but thinks more like a human brain. Neuromorphic computing is a type of computing inspired by the human brain. Instead of relying on strict step-by-step instruction like traditional computers, neuromorphic systems are built around artificial neurons and synapses. In the brain, neurons only fire when something important happens. Neuromorphic chips do the same thing. They use tiny spikes of electrical signals to communicate, making them fast, adaptive, and extremely efficient. While typical computers calculate every step in order, neuromorphic processor react instantly, just like how your brain reacts the movement you hear a sound or see movement. Imagine placing a human brain beside a modern computer. At first glance, the computer seems faster, but the brain is doing something extraordinary. It processes billions of signals every second, uses only about 20 watts of power, and it never stops learning. This inspired behind neuromorphic computing, a new kind of computer architecture designed to work more like the brain. To understand why neuromorphic computing matters, let's compare it to the traditional system. Most computers use the von Neumann architecture. In this system, the processor sits on one side, the memory sits on other. The data is constantly shuffled back and forth between the two. This is like having your kitchen in one building and your dining room in other. You can cook, but you can waste the time back and forth. For simple tasks, it works fine. But for AI tasks, imagine recognition, robotics, autonomous driving. This data movement become a bottleneck. It shows everything down and consumes huge amount of energy. Now, enter neuromorphic architecture. Instead of separating computations and memory, neuromorphic chips combine them into the same place, just like neurons and synapses do in the brain. Each tiny unit can store information and process signals. At the same time, this creates a system that must be parallel, incredible fast, and extremely energy efficient. Instead of single highway filled with traffic, neuromorphic chips are like entire cities of interconnected routes, millions of them all active at once. The magic behind this design comes from something called spiking neural networks, or SNNs. Unlike traditional AI models that process data continuously, SNNs only active when something meaningful happens. Picture a neuron staying quick until enough input triggers a spike, then in a burst of energy fires a signal to connected neurons. This event-driven processing means the chip only works when it needs to, just like the brain. It saves enormous energy while reacting real-time, making it perfect for sensory devices like camera, like microphones, or robots that needs to respond instantly. This is not just theory. Real processors like Intel's Lily and IBM's True North already demonstrate what neuromorphic computing can do. They can perform complex AI tasks using orders of magnitude less energy than traditional chips. image robots that think faster but run longer on battery, smart glasses that analyze the world without heating up, or tiny sensors that stay active for years on almost no power. Neuromorphic computing is a major step toward machines that just compute, they think more like us. In agriculture, this is a game changer. Picture a drone analyzing crop health instantly while flying, not sending photos to a remote server, but understanding everything in real time. It could detect nutrient deficiencies, water shortages, early sign of disease, or pest activity the moment it appears. Dexterous harvest robots become more precise with neuromorphic processors. They can recognize ripe fruits and handle them gently, almost like a human hand. Environmental monitoring becomes more powerful too. Neuromorphic sensors can be placed in forests, oceans, and remote ecosystems. Because they use extremely low energy, they can run for months or even years on small batteries. They only wake up when their sensors detect something important. They could detect early wildfire signals, track endangered animals, or monitor air and water quality, all without relying on huge servers. In industry, neuromorphic processors bring real-time intelligence to machinery. Robots can respond instantly to changes in the environment and adjust their movements without needing to stop. They can detect manufacturing defects on the fly, optimize processes, or coordinate thousands of moving machines with low energy. This allows entire factory and logistics centers to become faster, safer, and more suitable. So why is neuromorphic computing such an important emerging technology? Mainly because it solves three big problems in modern AI: energy use, adaptability, and speed. It gives us machines that don't just process information, they respond and learn, more like living brains. As the world faces bigger challenges in food production, environmental protection, and industrial efficiency, neuromorphic computing offers a powerful, energy-efficient way to create smarter, more responsible system. We're standing at the beginning of a new era, one where machines think not like computers, but a little more like us.